Could you tell us exactly what we will be covering in the upcoming lectures? So, we will try to cover some part of quantum information that's like BB84 protocol and things like that. And then we will try to cover some quantum algorithms like Grover, Deutsch, and in general quantum channels, and try to run some of the things like CHSH inequality and other things on quantum computers, and discuss more about transmon qubits and decoherence noise and stuff like that. So that's a broad overview of what we will cover next week. Does that answer your question, Priyanshu? Okay. Okay, I think everyone is here, so I'll launch the poll to for the attendance. Please take a minute to enter your name. Thank you. Rajneesh, I don't think there are any key features. You can use anything that that it's not necessarily that Qiskit is. The main reason that I was using Qiskit is that because IBM was giving free tokens, and Qiskit runs very well with IBM, and that's the main reason. And they have a lot of examples on Qiskit, but you could use other platforms if you want. You could also don't also have to run on just the superconducting qubits. There are also ion trap and other simulators that are available from Qubit. You could also use those if you wanted to. Um, yeah. Okay, I'll end the poll. Shafna, it's okay. If you didn't see the poll. Okay. Let's get started. So, in this lecture now, what I would like to do is I would like to or on the other hand, Qiskit runs complex algorithm. I'm not familiar with Circu as such, so I don't know if it can run complex algorithms or not. So I did not want to comment on that, but Priyanshu seems like he knows that very well. So, um, but I just like I said, Qiskit is I find that it is better. Okay, he searched it online. Okay, that's great. So let's get back to what we were discussing on Transmon qubits. I introduced Transmon qubits briefly, and today what I want to do is I want to go over that in more detail because whatever we have done so far, it is very theoretical. And although we have discussed some experimental things, I want to, before we begin with transmon qubits, I want to make some analogies and talk about some things in terms of measurement. So let us say we talk about mechanics, classical mechanics. So when you study classical mechanics like Newtonian mechanics, you learn it like, for example, without friction. And then later on, you say, okay, friction is, it is not zero. It doesn't, you cannot get rid of friction. And so you add friction as an extra force. And then you start adding more and more realistic things. But when you start studying mechanics, the thing is you abstract, that is, you conceptually switch off things like gravity or friction and just try to study some simple problems and then try to switch on friction, try to switch on something else, and then get actual mechanics out that is in real life. But unfortunately, in quantum mechanics, we don't do that in the sense that we talk about everything like we separate variables from time dependent, time independent, and then we talk about time independent Schrodinger wave equation, and we talk about measurements as if they don't take time. We talk about measurement as if the device doesn't perturb anything, and so you have to be very careful. So in fact, what happens when you make a measurement, like let's say I say we have a Stern-Gerlach experiment, let's say along some axis, right? When I say this, that means it's actually a magnet, right? So what is inside a magnet? It is some spins again, right? So those spins are magnetized, and that's what we call as a magnet, right? So let us assume, let us say this small magnet, just for the point that I'm trying to make. Let's say this is a small, very small magnet. There are a few spins that are pointing up. That is this some ferromagnet that we have here, right? It is magnetized, like you take some neodymium or whatever, and you magnetize it, and that's what you use as north and south poles. But they are ultimately spins, right? So now, when you want to make measurement, then that means that you are passing particles through this, right? So when you pass particles to that, you sort of ignore the changes that happen in the detector itself. But what actually happens is that the spins in the detector become correlated with spin of whatever is passing through. So in fact, the detector gets entangled with your system. So remember that we saw that correlations are entanglement. So whenever you measure something, then your ensemble changes. So for example, if I say, look at particle in a box, let's say I have a potential well and I have some particle, right? So when we talk about this as an ensemble, this as a state, as a preparation technique, that means when I prepare it, it could be at this position, or it could be here, it could be there, wherever, right? So different possibilities. So I'm conceptually imagining an ensemble, right? So similarly, when you make a measurement, you have an ensemble even for your device, right? So when an electron is passing through the Stern-Gerlach experiment, let's say, right, then it is actually what, when you say spin up, that I passed some atom and it came out as spin up through that spin up hole when I filtered it. What I actually made is, at the bare minimum a tensor product with the device, right? At the bare minimum, if it is tensor product, it is not entangled. But usually you would end up making, this is your particle, and then this is your device. So you would make it into a not necessarily a product state, separable state. So your measurement itself can entangle with the system. So you have to, when you say like you want to repeat the measurement on that particle, then you are not repeating it on particle, because your device is not as a product state. It is actually becoming correlated, because that's how you say you are measuring. Because if your device, whatever pointer you have in your device is not correlated to whatever is coming in, then it's not a measurement, right? So you have to be very careful there, that whenever we measure, it can get entangled there. It may be possible that it is not entangled, but you have to consider device as a part of your system now, whatever the spin up. I hope that makes sense. Any questions on that? Okay, no questions. Do you all agree? Okay, I need some feedback from you. Okay, okay, I see a couple of yeses, 3, 4. Okay, great. So bear in mind that you could get entangled with the device. That's very important. So then your state preparation becomes particle plus device. Um, uh, Give me a second, please. Sorry, the screen got disconnected there for a minute. It's back on now. Okay, so now we are going to look at the practical way of realizing these qubits, which I talked about transmons. So before that, we have to talk about Josephson junction, which is the key element, key nonlinear element for realizing qubits. So we briefly talked about this. So a Josephson junction has two superconductors. So here you see them in the gray color that are sandwiched with a oxide or an insulator layer. So when we say superconductor, these are basically any metal like aluminum, niobium, all these metals would superconduct at very low temperatures. And we anyway need to be at low temperatures because we want to filter out noise and decoherence. So you could use metals like aluminum or niobium. It doesn't have to be some fancy superconductor. So these are two superconductors that are sandwiched with some oxide or insulator layer. So these things exhibit what we call as macroscopic quantum effects, meaning that I could have these are still very small things, but still what we would see is that the superconductor insulator superconductor junction, which is called the Josephson junction, exhibits some interesting properties like current and voltage. So here you could consider it like you have some wave function that can macroscopic wave function of superconductor A, which is at the bottom, and on the other side you have some macroscopic wave function of the superconductor psi B, and in between you have sort of a potential well that is coming from the insulator. So in general, in superconductors, we have what we call as a Cooper pair, right? So here the pairing arises, what we say is due to an effective interaction between Coopers, between electrons and phonons. So two electrons are sort of paired through lattice vibrations, if you want to consider phonons as lattice vibrations, right? And then these are like spin up and spin down with opposite momentum. And so then these behave, each electron itself is a fermion, right? Which means that you cannot have more than two electrons in the same uh, uh, K state, one with spin up and another with spin down. But bosons, any number of bosons can occupy the state. So they condense into a single macroscopic quantum state, right? And there is something called the energy gap that protects these Cooper pairs, which leads to zero resistance and what we call as macroscopic quantum coherence. So this delta is called the superconducting energy gap, and in BCS theory, which we are not going into great detail, right? Near the Fermi surface, you have these electronic states that do not exist for a gap. There's a gap that opens up within delta. This you can physically think of as the binding energy of, okay, Satvik did not get the graph. So it is just a schematic, Satvik. This is just showing that you have some macroscopic state on the superconductor on the left. You have some macroscopic state of the superconductor on the left, on the right. And in between, there is a potential well that is given by the insulator. So you have two superconductors with some macroscopic quantum state. And this macroscopic quantum state belongs to the Cooper pairs in each superconductor. That is what is psi A and psi B. And in between you have an insulator which acts like a potential well. Does it explain the graph now, Satvik? Okay. So
Sir,
yes.
sir, I was thinking with respect to the graph, were we talking about its application in the computer?
Which graph?
Sir, this very graph of the SIS junction.
Uh-huh.
Sir, are we talking about its application based on this graph?
I mean, we are not talking about any application. It is not a graph. It is just a schematic to show what a superconductor insulator. It is not real data or anything. Like it is just
Okay.
a schematic to show that you have like a macroscopic state on the left and a macroscopic state on the right. But in between, so on the left and on the right, it is superconducting. In between, it is an insulator. Just making a point. No application, nothing. We're just talking about Josephson junction. That's it.
Okay, sir. Okay, sir. Thank you.
So this no electronic states exist around the Fermi level. So what this physically means is you can think of it like the binding energy of a Cooper pair. So this delta is like a collective property. It's not an individual particle energy. So it is like the average energy that you can think of to excite quasi particle from a condensate. So because no states exist between plus or minus delta, that means that you are very stable against thermal fluctuations, and then you can get basically superconductivity. So we are not going to go into BCS theory in the superconductivity part, but I just wanted to briefly mention that in each of these superconductors, even if you do not know BCS theory, it is okay. All that you need to know to understand this lecture is that in each superconductor, once you are below a certain temperature, that is, once they start to superconduct, then they have the electrons pair up into Cooper pairs, and all Cooper pairs condense into one state, right? Because Cooper pairs behave as bosons and not fermions like electrons. And these Cooper pairs, we can count how many Cooper pairs are there, right? We can call them as like n Cooper pairs, right? N superconducting Cooper pairs. That this is the density of super pairs, superconducting Cooper pairs, and we can describe each superconductor with a macroscopic wave function, right? Because all the Cooper states are condensing into one state, right? So then this macroscopic state I am writing as, let's say psi of r is square root of ns, and I'm adding a phase factor. So recall we talked about global phase and relative phase. So when I write like this for one superconductor, this would be a global phase, right? This would be a global phase. That is just for one superconductor. That is, if I were to take psi square, right, then I would just get ns, right? This e to the power I phi r, whatever phi r is, that phase, it does not matter for the statistical outcomes which have to do with the probability. Are you following me? So this is a thing that was introduced by Ginsburg and Landau. Block wave function. Okay. Ginsburg, Landau, and in so I think Priyanshu, we're not talking about any block wave function here. We're just talking about macroscopic wave function. It should not be confused with like individual electron wave function or a periodic lattice wave function. Here we are just talking about just a macroscopic wave function in a very phenomenological way. So so here psi of r, when I have a phase here, this global phase does not matter because when we square it, we just get ns, right? So the phase phi r, however, is related to the supercurrent, we will see, because when we talk about the probability current, then you have terms like probability current would have terms like psi star gradient psi minus psi gradient psi star. So these terms would have this gradient of phi, which has the phase, and we will see some effects of this phi on the current. So, but basically this psi of r right now on this slide, what you need to understand is the psi of r describes a coherent condensate of all Cooper pairs, which is like a Bose-Einstein condensate. So now in our Josephson junction, what we have is we have two superconducting layers. In between, we have an oxide layer. For each layer, although they are the same material, so let us say I have on the top, I have let's just say aluminum, or it could be niobium, whatever that is. And then let's say this is aluminum oxide, um, A2O3, whatever, and aluminum, right? Let's say this is our Josephson junction. So we go down to a temperature that is below the critical temperature for aluminum to superconduct, and at that time at that temperature aluminum is superconducting. So this has Cooper pairs, right? So this also has Cooper pairs, and so this I am representing as psi A, and this I am representing as psi B. And so this would have some psi 0 e to the power I phi A of r, and this will have some psi 0 e to the power I phi B of r. So when we look at this, what we are trying to say is, let's say we have two aluminum layers that are exactly same thickness, they are the same width, same length, everything is same, but they're two different layers. So when we cool it down below the critical temperature, that is our state preparation procedure. That means when I'm below TC, I'm forming Cooper pairs. But those state preparation procedures, while they lead to same statistical outcomes, they are not exactly same. They have a phase, and that phase need not be the same. So the Cooper pair density may be the same, but the phase may not be the same. right? So there could be difference in phase. So that's why we are labeling it as e to the power I phi a and e to the power I phi b. In fact, if we have a phase difference, then what we say is we do get a Josephson current across the junction. So if you solve the Schrodinger equation in the three regions, do the boundary matching and all that, then you do see that you get a super current that flows through the insulator as this, where JC is the critical current. That is, if you go beyond JC, then your superconductivity is lost. So superconductivity exists only till a maximum critical current. So if you go beyond that critical current, then you begin to see resistivity. So that critical current is what we are calling as JC. So although these two superconductors are the same material and we are preparing them same exact way, there is some difference in their state preparation, which is in the phase factor. If I have just one phase factor as a global phase, it doesn't matter. But if I have two superconductors which are sandwiching an insulator, then the relative phase matters. And that relative phase is what we see here. Phi A minus phi B is the relative phase, right? And so the current that flows through this Josephson junction depends upon that relative phase. This relative phase is very, very important because this relative phase is what is going to allow us to tune our qubits. So the Josephson current relation then is depends upon the barrier height, how the insulator is, it depends upon how thick this is, and it depends upon all those factors which we don't need to go into. We main thing that we need to understand is this, that the Josephson current, if you have two superconductors, there is a current flowing through the insulator that is proportional to the phase difference, and that phase difference is coming from the difference in the state preparation, the ensemble of two, although we have done everything exactly the same way, right? There is some difference between those, right? And it is that relative phase that matters. Any questions so far? Okay. So the phase phi of r, it does not belong to one particle or one Cooper pair. It is, we're describing a condensate. We're describing an ensemble of Cooper pairs. Again, when I say an ensemble of Cooper pairs, again, it is not a, so what the entire here in this case, we are sort of thinking of the entire macroscopic state. Like if there are 100 Cooper pairs, we're thinking about one wave function for all the 100 Cooper pairs. You see, so it's a when I talk about ensemble of Cooper pairs, it's not just 100 Cooper pairs. It is multiple copies of these 100 Cooper pairs. That's the ensemble of Cooper pairs that we're talking about, right? So when I prepare these Cooper pairs, then they are going to be having some phase difference phi r, and this is not coherence of a single Cooper pair. It encodes collective coherence of all Cooper pairs in my state preparation. It's a macroscopic quantum order, right? It's a statistical parameter that is reflecting long range order in the entire superconducting ensemble. Yes, it is a Bose-Einstein condensate. That's right. So all the Cooper pairs are. I thought I said that it is a Bose-Einstein, like a Bose-Einstein condensate somewhere. If I didn't, yeah, analogous to a Bose-Einstein condensate. So So then this phi is not again for a single particle. That's the thing that I want you to understand, that it is different preparations can, although they yield the same density of Cooper pairs, they can yield a different phase. And these relative phases between the ensembles is what lead to observable effects. Okay. So the statistical meaning of this thing usually is described as tunneling. That is like this is superconducting, this is superconducting. So one Cooper pair tunnels through this to aluminum oxide and then tunnels into the other aluminum, and that's how you get the current is often what people do. But I do not like the word tunneling, right? Because it is not a single particle state. It is what we are describing. The Ginsburg-Landau is not a single particle state. It is an ensemble macroscopic state. So this J that we are talking about, the current through the Josephson junction, is an ensemble average current density. It is not a single pair event. And the dependence on sign, it has these two macroscopic wave function in that, right? So this Tunneling is the traditional term, but what we would say in statistical interpretation is it's a coherent coupling between two superconducting ensembles. There, we are doing everything exactly the same. We made these things, we cooled it down, but they're two different aluminum layers, right? So there may be like some mismatch, some differences. That is, one aluminum layer, this top aluminum layer is in touch with the top of the aluminum oxide. This one is in touch with the bottom aluminum oxide. So they are somehow little bit different. So their phase is little bit different. So there is some coherent coupling between these superconductors, which is coming through as a current due to the relative phase difference. So it is not because one Cooper pair is tunneling, although it is described like that for sake of simplicity, but it is not really literally one Cooper pair is tunneling. So recall that one state is a reproducible preparation that fixes all the probability distribution. So in superconductors like this, when we say when we say preparation, right, it is cooling below Tc and electrons near the Fermi surface are becoming correlated pairs, right? This is what we are calling as the condensate, and we are fixing the statistics, but we are not fixing the phase, right? That is the key point, that preparing Cooper pairs, we're preparing an ensemble state. Again, state is not one single observable. It should encode information about all the observable, all the probability distributions. So our state preparation technique here is coat a thin layer of aluminum and reduce the temperature below Tc. That's it. That's our state preparation technique, right? So you can think about just simple probability current, right? You may have seen this in standard quantum mechanics, like I talked about psi star gradient psi minus psi gradient psi star, right? And if you have a phase, you can see that the gradient of psi should give you gradient of whatever, square root of ns e to the power I phi, then you get square root of ns I gradient of phi e to the power I phi. So you see that the supercurrent will depend upon the gradient of phi. So if there is a difference in the phi between top and bottom aluminum layers, then you will have a probability current density. And that is what would be seen as superconducting current, Josephson current, that is going through. So in fact, you can sort of derive it in a very simple fashion by kind of talking about the total wave function for the Josephson junction as a combination of psi A and psi B, where psi A and psi B again are macroscopic wave functions. And we can compute the total current there through the probability density. And then you can see that whatever this term is related to the critical current, and you get some sine delta term, right? So this is again an ensemble average flux of Cooper pairs arising from interference of two macroscopic phases. The phases in top and bottom aluminum layers is different. So then we also have another Josephson relation. The first Josephson relation is this, that there is current flowing through one superconductor to the other, which is related to the critical current, and delta, which is the relative phase. This delta is the relative phase difference between phi A minus phi B, or phi 1 minus phi 2, whatever you want to call it. It is the relative phase difference. There is also gauge invariance, which we are not going to great detail here. But to keep it short, this gauge invariance means that you get this phase, the way this phase changes under a potential is given by this, right? For gauge invariance. And so if you have Cooper pairs, in a Cooper pair, you have two electrons, so you consider Q to be 2e. So if you plug in Q is equal to 2e, you can see that d phi by dt is like minus 2e by h bar by v, right? So the relative phase difference would go as this. The relative phase difference would be like delta dot, that is the time derivative, d delta by dt is 2e by h bar times v. So if I rewrite that, I can write this as v as h bar by 2e delta dot, right? And this h bar by 2e is what we are calling as phi naught, or phi naught by 2 pi, or however you want to do it, just some constant. Some people just use phi naught, some people use phi naught by 2 pi. Either way, it is fine, but it is just a constant basically. The thing is that the voltage is proportional to the potential. Again, this is coming from here Um, the V is coming from the superconducting junction that we saw up here, right? From here, right? Whatever is in the insulator. And that basically determines how our phase difference evolves, right? And so we have this V is equal to the rate of change of the phase difference. So these are the two Josephson equations which we are going to deal with. Again, these represent not single Cooper pairs tunneling across, but these are ensemble average. So when we are measuring current, it is not a single particle there, right? So these are ensemble average properties that we are talking about. And delta is the relative phase difference, right? So voltage appears only when phase evolves with time. So if you have phase that is not evolving, you have a constant phase, right? Then you may have zero voltage because there is no voltage difference between these things. So only when phase evolves, then you would get this statistical effect of voltage. So now we have these two I and V relations. So what we could do is we could do di by dt, right? So we have that I is equal to IC sine delta. So I can do di by dt, do the time derivative. IC is a constant parameter, so I would get IC cosine delta d delta by dt, right? But we know that from the voltage relation, right, this d delta by dt is, I can write this d delta by dt from the voltage relation as 2 pi v by v naught, phi naught. So I can plug this into di by dt, right? So then I would get di by dt as IC cosine delta 2 pi v by phi naught in the Josephson junction. The reason we're doing that is that we want to draw parallels with inductor. So in an inductor, the voltage, is goes as LDI by dt, right? So we have this di by dt. So if we call this term Lj, right, then we can write Lj as V by di by dt by V. Is it right? No, Lj is V by di dt, right? So I can write the inductance of the Josephson junction as V times di by dt inverse, right? So then I can just plug that in, right? So then that would be V divided by IC cosine delta 2 pi phi naught would go up here, and then I have another V here, so that cancels out. So I get phi naught by 2 pi IC cosine delta. So this Josephson junction acts like a inductor, and that inductance is given by this phi naught. And the main thing is I control this inductor using delta, the relative phase difference. Yes, the inductance is not changing the phase. The inductance is coming because of there is a relative phase difference. No, it doesn't change the inductor. The inductance appears because there is a phase difference between the superconductor 1 and superconductor 2, right? So this is what is causing this. It is not just because we have a relation, it is not like, this is causing this, right? So it is delta. It is not changing. Without delta, you don't have an inductance. It is delta is leading to the inductance, right? So if there is phase difference, then you get inductance. Not that inductance is changing the phase. Does that make sense, Priyanshu?
Yes, Professor.
Okay, thank you. So the key points is that whenever we prepare, when what we call as a state preparation procedure, we're fixing the probability. So when we prepare the state here, that is go below the superconducting temperature, we can only prepare the state up to a particular phase. And there is a phase difference between the top and bottom layers of the Josephson junction. And if there is that phase difference, then because of that phase difference, we get an inductance in this Josephson junction. If there is no phase difference, then there is you don't get that variability, right? So you don't get that current, right? So if this phase difference is zero, then there is no current. Sine zero is zero, right? So then we get because of the phase difference, we get something like this. So the way I wrote here is because I is equal to IC cosine delta, right? Then I can write sine delta as I by IC. So cosine delta would be 1 minus square root of 1 minus sine square delta, which would be square root of 1 minus IC by I by IC square. So that's all I am substituting here, 1 minus I by IC square, right? So that is the inductance, right? So now then what we want to do is we want to calculate how much power is stored in this inductor. So then we just do IV, and the energy, if you want to compute, then you integrate that over time. So we are simply going to take I, which is IC sine delta, and we saw that the voltage is phi naught by 2 pi delta dot d delta by d. And so then if you integrate, and then you just basically get this constant out. IC is a constant, phi naught is h bar by 2 pi. So sorry, h bar by 2e. So you get those constants out, and you get the total energy as 1 minus cosine delta. Again, here we're defining EJ as Josephson energy, which is IC phi naught by 2 pi. So this is a constant, right? But this has to do only with the inductor part. So we what we basically said is when I make a Josephson junction and there is a relative phase difference, we have an inductor, and that inductor has this much energy. Notice that this EJ is a constant. So it is just like shifting it up or down, the energy level shifting up or down. So you will see that I will just write this as a constant, or you can ignore it sometimes because that's not really dependent on anything. It is just a constant term. IC is the critical current, phi naught, 2 pi, they are all constant. So EJ can be treated as a constant. So what does this mean statistically is that these are not single pair quantities, but collective energy scales of the entire Cooper pair condensate. But these have reproducible dynamics in the sense that when I have the total Cooper pairs, there is a relative phase difference between them, but they can that relative phase difference can lead to a current which has an energy associated with it. These are not one single pair Cooper pair having an energy of that much that is going crossing the junction. You should not think about it like that. These are collective energy scales, not single pairs. But in addition to having the inductor, because we have our structure is we have superconductor, insulator, and another superconductor. You see that this is like a dielectric capacitor, right? You have two plates, and in between you have an insulator, right? So you also have a capacitor there. So we also have to consider the capacitor energy. What we considered so far was the inductor energy. So you know that capacitor, the energy stored in a capacitor is the charge stored in the capacitor divided by 2C. So if you have like n Cooper pairs, which we saw in our macroscopic wave function, each Cooper pair has a charge of 2e. So we can say the total charge is then 2e times n, right? And this n is actually energy number density. So u is energy density, you can think of it. And so then we can obtain an expression for the capacitive energy, right? U capacitive energy. So that would be q squared by 2c, qe. So you simply put 2en squared by 2c, which we would write it as 4e squared by 2c n squared. So it depends upon some n square term. That is the square of number of Cooper pairs. So energy depends upon the ensemble statistics of how many Cooper pairs occupy the junction. Again, it is not single Cooper pairs tunneling and leading to the current. So we can also write this as we take this E square by 2C as EC, and we write the UC as 4EC n square. And we have written UL from the inductor as EJ 1 minus cosine delta in the previous derivation, where EJ was IC phi naught by 2 pi, right? All are constants. IC, phi naught, and 2 pi are constants, right? So the reason we are writing that is, this is, some sort of a fundamental qubit. And the C is the geometric capacitance of the whatever you have here, right? The insulator, you have the distance, the thickness, and the area of the thing. So that's the capacitance. So then now we can write the total Hamiltonian for the Josephson junction, right? We have the capacitive charging energy and we have the Josephson energy. We just basically combine that. You can think of this as potential energy plus kinetic energy, right? And so if I combine that, remember that this EJ is a constant. So I can just write the full Hamiltonian as 4EC n square, which is coming from the charging energy. And I'm only considering this EJ cosine delta term because the other term is constant. I'm just writing it as constant. So here I have two conjugate variables. That is, one is the relative phase and another is the Cooper pair. So these are conjugate, meaning that I can either determine the relative phase or I can determine n. That is, if I perform multiple experiments, recall that when we studied the uncertainty relationship, like delta x times delta p is greater than h bar by 2. What that means is, let us say I have some state preparation technique, whatever this is, some state preparation technique, and some particles are coming out. On these particles, I may keep making measurements. I measure their momentum or I measure their position, and then I make statistics, right? And then I see the position histogram. Some land up here, some land up there. Some histogram I get for position. This is the position histogram. This histogram will have some delta x, and similarly, you can create a delta p for a momentum histogram. But these are multiple measurements on identically prepared system, right? So similarly here, you can think of delta as the momentum, n as the position. So, okay. So n as the position and delta as the momentum. So if I measure the relative phase multiple times on identically prepared ones, that is, I measure the delta on superconducting junction. I reset it, I measure it again, reset it, measure it again. I collect the statistics, right? And then the delta I'm going to get, sorry, this is delta delta, and delta n is going to be greater than or equal to h bar by 2. That is the uncertainty relation, or what we would say is that they are conjugate variables, right? This is similar to a non-linear quantum oscillator, right? So you can see that you have cosine delta here. That is why we are calling it non-linear, right? Because cosine delta is oscillating. It is not like it is oscillator, but it is not a harmonic oscillator, right? Harmonic oscillator would be something like half kx square, right? If we had a normal inductor, let us say normal inductor, not the Josephson junction. If we had a normal inductor, what would happen, right? Let us say you just had a normal inductor, then you would have the capacitive energy would be something like, would be related to q square by 2c, and the inductor energy would be related to half Li square. If we did not have the Josephson junction, if we had just a normal inductor, then this would be like a harmonic oscillator. This would be harmonic. So then the potential will be parabolic here, right? You have parabolic. So if you have a harmonic oscillator, the problem is the energy levels in harmonic oscillator are equally spaced. The difference between energy levels is half h bar omega. So if they are linear equally spaced, that's a problem, because when I try to control the qubit, I cannot say whether it is getting excited from state 1 to state 2 or state 0 to state 1 or state 2 to state 3, because all the things have half h bar omega. So if I try to excite it with some half h bar omega microwave pulse, then I cannot be sure that I am exciting it from 0 to 1 or 1 to 2, because all the energy levels are linearly spaced in a simple harmonic oscillator. The advantage of Josephson junction is that the Hamiltonian has this cosine delta term, which is not harmonic, right? So it's not a simple harmonic oscillator, it's not a parabola, right? And that's what is the important part of why we are using the Josephson junction. So it is a non-linear quantum oscillator. It is still an oscillator, but it is not a simple harmonic oscillator. And its quantized energy states would not have equal spacing. Are you able to follow me? Any questions? Okay. Okay, got it. But this is whatever I have described so far is like very ideal Josephson junction. But in reality, things are not that easy. And as an experimentalist, we always come back to reality, because whenever you make a measurement, right, you have to think about time. You have to think about resetting the detector. You have to think about entanglement with the detector. Similarly, when we make a real Josephson junction, it is not, again, tunneling in quote unquote, whenever you are looking at tunneling, because a lot of people describe this as single Cooper pair tunneling, but the Ginzburg-Landau wave function is not for a single Cooper pair. The Ginzburg-Landau wave function is describing a macroscopic state. It is not for a single Cooper pair. So bear that in mind. So a realistic Josephson junction is, you can consider that as it has some resistance. The resistance kicks in only above the critical current. Below critical current, you are superconducting, so there is no resistance. But above critical current, you have the resistance. The X is the symbol for the Josephson junction, and it also has capacitance, as we have seen. It has a capacitance and inductance. So this is how we can do what we call as cavity QED, right? So, or circuit QED, not cavity QED. My bad. So we are expressing this Josephson junction as a real junction. So this is an ideal Josephson junction. Ideal Josephson junction wouldn't have any capacitance. So we combine the capacitance with the ideal Josephson junction. Ideal Josephson junction would have only the inductance. So this capacitance and resistance, if you go above IC, that this is the symbol for the real Josephson junction. So now we can model this real capacitor Josephson junction that looks like this, right? So I have Josephson junction, I have the capacitor and the resistor, and I have some voltage source, right? So these three are in parallel, right? And then you have capacitive current coming from the capacitor, Josephson current. Remember, Josephson current is coming from the junction. So in the element here, what you see here is that when we connect these capacitor in parallel, these two things are physically the same thing. These two things are the superconducting layer, insulating layer, and superconducting layer. This is what we are representing like this, below the critical current. So these are in parallel, meaning that the capacitor charging and the inductor current are in parallel. It is not like one is happening and then the other is happening. So that's why they are in parallel, right? So we get these currents. This R may not be relevant when we are below the critical current, but in general we are including it, right? Just are when we are above IC, this resistance will kick in. When we are below IC, it is just these two terms. So now you can just do like Kirchhoff's law only, Kirchhoff's law only. You can just do this. You can see the total current. It will be a sum of, at this junction, the sum of IC plus IJ plus IR. IC is the capacitive current, which is CdV by dt. IR is the resistive Ohm's law current, V by R. And Josephson current is depending upon the relative phase difference. So the real quantum part is in the Josephson junction, because this delta is coming again from the state preparation. I hope the reason why I kept on talking about state preparation has come to use now after so many lectures, and you are able to correlate to, I'm saying correlate, you are able to relate to why this delta is coming in, right? That is the relative phase difference. It comes from how you prepare the state, right? The global phase difference doesn't matter. So it is coming purely from the ensemble and not from single Cooper pairs. So then we can write this, right? And so I can move this I over to the next side, and I know how the voltage should be in the resistor, that or in this capacitive element, because I have the second Josephson relation from gauge invariance, that is voltage is proportional to delta dot, the time dependence of the phase difference. So see that if there is no time dependence of the phase difference, these two terms are zero, and all the current we will have is Josephson current. But if the time dependence of the phase difference is not zero, then we will have these elements. We will have to consider the resistive part and the capacitive part. Are you able to follow me? Any questions? No questions?
Uh, Sir, this Ohm's law current, we are getting it above the superconducting state, right? Like so critical temperature basically.
Right.
And this
No,
junction
sorry,
voltage.
sorry to interrupt you. Not about So you may still be below critical temperature, but even below critical temperature, if you surpass a particular current density, then your superconductivity is destroyed. The Cooper pairs are destroyed. So remember that Cooper pairs have the delta that I talked about in the beginning, the other delta, the superconducting gap, right? That would be gone. That, yeah, above the critical current, the Cooper pairs are broken. So you may still be T may be below TC, but if you are above the critical current density, then the Cooper pairs are broken and you are not superconducting anymore, and you have to consider resistance.
Oh, okay, okay, okay. And we are considering both voltage equal, like in IC, the voltage due to the junction and the this ohms voltage.
It is the same thing. So this is the Josephson junction only. I'm writing it as three things in the sense that in reality, this Josephson junction is only one Josephson junction. That is this. You have a
So
superconductor,
it's a
you have insulator.
schematic
Yeah,
cycle.
schematic. You are writing it as three. But those three things are in parallel, meaning those are the same thing, right? I'm just writing as three elements. That's it. Does that make sense? So it's the
Yeah,
same
yeah.
voltage, right?
Okay, 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 okay.
Yeah. So that's why we're putting this phi naught by 2 pi here, right? Any other questions? So now you see, look at this one. This looks like a harmonic oscillator. Is everybody familiar with this damped driven harmonic oscillator? I'm assuming so,
Yes.
right? Right. So if you have force is minus dou u by dou x in one dimension, right? Sort of Newton's law, right? Or I should not write maybe like that. So force is minus grad u, you could think, right? And then so also it is also equal to d square m dp by dt, right? And so force is dp by dt, which would give you m d square x by dt square, right? Which is what we are calling as mx double dot here, right? So I don't like to say force is ma or mx double dot because mass could also change, right? So technically force is defined as change in momentum. So you have mx double dot, that's the force that is equal to this whatever the potential, right? And then you have this kx dot is the damping, and so this is like a damp driven harmonic oscillator. So you can compare these and you can see that mass should be equal to the x dot term. So the capacitance behaves like the mass, and the drag is related to the resistance. Okay, there is Saptagiri, you said no, no for the damped harmonic oscillator. Yes, okay. So yeah, so you can, so basically if you have just a normal oscillator, you just have F is equal to, this would be the harmonic force that you are applying. So let's say if I have a spring and I have some mass attached to it, right? Then if I push it, right, then you compress the spring, right? That force would be equal to minus kx, right? That is how much you compress it or how much you expand it, right? So then you would have mx double dot, that is the coming from Newton's second law, equal to minus kx. So for a simple harmonic oscillator, it would be just a normal oscillator. This would be the equation, right? And then if you have damping, that is if you consider air resistance or whatever, then you have to add a term, a drag term, that is related to x dot. The drag term is related to the velocity, right? So that is the drag term that we are adding with d. So in general, in reality, it would have this drag term x dot plus this du by dx is the force kx. In this case, in spring and mass kx. If it is some other harmonic oscillator, it would be whatever that force is. So in general, you can write that as the gradient of the potential energy. Does that help? So we're just basically comparing. We are comparing this mass to this capacitor, the drag to the resistor. So you see, that's why it makes sense, right? The resistance is what drags it back. That's why we call it a resistance. And then Then the energy, the potential, I can write it as a minus I plus I sine delta. So I'm comparing these two equations. But if you compare here, this x in case of the oscillator is the position of my mass. Here delta, the variable that we are considering, is the relative phase difference that is coming due to difference in the state preparation. Right? Same superconductors, difference in the state preparation. And it is in fact this difference in the state preparation that we are using as our variable, this delta. It is not like position of a real particle. Are you able to appreciate that? It is not like a single particle. It is the phase difference that we are trying to talk about, right? So when we talk about mass here, it is an effective mass. It is an effective damping term. And then we can compare this energy term, and you see that the energy term should be equal to this whatever minus I plus IC sine delta. So if I take IC as a common factor, I get this. So you can do a simple integration and you can see that this is the potential, and this potential is called the washboard potential. You can look up washboards in the and see how they look like. And I don't think washboards are used anymore. So but you can see that we have a potential that is cosine delta. That is why it is not harmonic. Harmonic means you will have like x square. Like if, for example, here in harmonic oscillator, the potential is kx, right? So here, if I calculate the potential, I would get half kx square. Then I would get basically parabola where energy levels are equally spaced. If energy levels are equally spaced, then I have a problem because I do not know whether I'm exciting from 0 to 1 or 1 to 2 experimentally. So I do not want a harmonic oscillator. What I want is a not harmonic oscillator. And that's exactly the reason why we are picking this Josephson junction and how we got this cosine delta. So I hope it has become clear what delta is and what this potential is. This delta is not to do with, how do I put it? Like in harmonic oscillator, it is, when I talk about x, it is the position of mass. It is position of one particle. Here delta is not like that. It is a generalized coordinate. It is the phase difference that is coming in due to the difference in state preparation. And it is not due to single Cooper pairs. It is an ensemble effect. I mean, it is really beautiful if you understand what that is. I hope you are feeling the same joy that I am feeling. Okay. Um, Been ages. Okay. Is everybody following? Yes. Yes. Okay. Cool. So then now, if you look at this washboard potential, we can plot it as a function of delta. So if I by IC is 0, so if I by IC is 0, that is that there is no current, right? If I set I to be 0, then I by IC is 0. Then my potential will just be some cosine. So you see some cosine, right? Some cosine. So it starts with like non-zero. At 0, delta 0, it is -1, right? So let's write when I by IC is equal to 0, then my U of delta would simply be minus IC cosine delta. You cannot set IC to be 0. IC depends upon the material, right? But a total current is 0, right? So then when delta is 0, right, your U of 0 would be simply be minus IC, right? So you see that is the minus IC that you are starting from here. And then you have a cosine, right? So when IC is there, if I park at some delta, if I maintain a phase difference of 2 pi between the two superconductors, then I can trap the, that I am in this minima of the potential. This you can think about as a virtual particle. The phase difference, it is not a real particle. It is just the phase difference. That meaning that if I have a 2 pi phase difference in the way I prepare the state of the top and the bottom superconductors, then I can take that generalized coordinate like a virtual particle. There is no real particle there. Just treating it as a virtual particle, right? That means that there is no current flowing through the thing, and there is just minima in the energy, right? But if you have I by IC not equal to 0, if you have in fact I by EC equal to 1, you can see that it changes, right? Then you cannot trap anything in between here, right? So often people describe this as you're trapping a Cooper pair here, but this is not a Cooper pair. This is a virtual, like a delta is a generalized coordinate. So please do not confuse that at particular delta 2 pi you're trapping a Cooper pair. It is not related to a single Cooper pair. It is related to the ensemble, the macroscopic wave function, right? Is there any question there? Okay. So basically, we have a minima when I by IC is less than 1, right? Even here you have some minima, right? So you can have the phase particle is trapped. This is not a Cooper pair that is trapped, and it does not evolve in time when I by IC equal to 0, meaning that uh, there is no voltage drop, right? Recall that voltage drop is like goes as delta dot, excuse me. So there is no voltage drop. But when I by IC is greater than 1, that means the current is greater than critical current. So when I by IC is less than 1, that means I is less than IC. So the critical current is less than, the current is less than critical current. So that means you're still superconducting. So you have no voltage drop. But if you have I by IC is greater than 1, then I is greater than IC. So you're breaking the Cooper pairs. So you will begin to see breakdown of superconductivity, and you will get some resistance. So voltage will not be zero anymore. So you say that this phase particle is rolling down, but it is not a real Cooper pair. No, it doesn't behave as a harmonic oscillator. That is not right, because it looks like a harmonic oscillator, but it is still cosine delta. Because if it behaves like a harmonic oscillator, you can sort of, for approximation you can say like that, but the important point here is we don't want equal spacing between energy levels. If it behaves like harmonic oscillator, then we will have equal spacing of energy levels. We are going through all these lengths to build all this stuff because we don't want harmonic oscillator. Does that address your question, Priyanshu?
Yes, yes. I mean just a slight approximation in sense.
You can do that like that, but in reality we are not going to use it where it is harmonic. So we want to use it where it is anharmonic, so we can definitely isolate two states for the qubit.
Okay, okay.
Yeah. So overall, what we want to say is this Josephson junction is like a nonlinear oscillator where we are treating phase as a particle in a tilted washboard potential, and voltage arises when current is greater than the critical current because the Cooper pairs are broken. But this particle is not a single Cooper pair. This phase is the particle that is like a virtual particle. It is the relative phase between, it is the relative difference in the ensemble state preparation that we are using. So that is why whatever we have discussed in state preparation is important here to understand. The macroscopic wave function has the phase difference. It is the macroscopic wave function phase difference, the relative phase difference, that we are trying to tune by tuning the Josephson junction, right? So this delta is not a literal coordinate. It is a collective parameter that describes the ensemble of Cooper pairs. It is a statistical metaphor.
Professor,
Yeah.
can we also tune the number density of Cooper pairs so that by the conjugation
Yes.
we
Yes.
can also control the phase like indirectly sense, in an indirectly sense?
Right. You could. It is the same thing. So it is like I said, they are conjugate variables. So you could talk about the Cooper pace, but it is not, the current is not cannot be considered like the Cooper pace tunneling, although it is said like that. But here the delta, the relative phase difference, in the sense that, like, if I take one superconductor, I can make super Cooper pairs. Having Cooper pairs doesn't guarantee the current. What guarantees is the phase difference. So if I have two superconductors with no phase difference, then I have Cooper pairs, but no current will flow. Is that making sense?
Yeah, yes, yes.
Yeah. So that's why we are sort of analyzing it in terms of delta, right? So these are not the single particle measurements. Nowhere in quantum mechanics we are always considering statistical outcomes, right? So again, you have statistical minima. It is all ensemble average statistical outcomes, right? So we are talking about delta. So you can think about this as a mechanical energy, mechanical analogy. Like for example, if I were to give you a mechanical energy analogy, imagine a pendulum of having a rod of length r. This r is the rod, radius r, and it is attached to a mass, right? And it is rotating like this. And this phi is the angle of rotation, right? You have pinned it here at the center, and it is rotating, right? And so you have two dynamical variables. One is the angular momentum, and another is the phi, right? So we can the gravitational potential energy of this pendulum will depend upon the angle phi, right? So the gravitational potential energy would be mgr phi, cosine phi, and and the kinetic angular momentum would be L square by 2mr square, right? This is the moment of inertia, right? And L square, right? You get L square by the whatever the moment of inertia, and you can write that Hamiltonian. So you can compare, right? The angular momentum is like the Cooper pace, and the relative phase difference is like the angle of the pendulum, right? That is what you are considering. So having mass or angular momentum is not the one that we are tapping into. What we are tapping into is that for having, so if you have mass and the rod of this thing, but it is not oscillating, there is no meaning to it. If I just have this rod and the mass attached but it is stationary, right? Then there is no point in this Hamiltonian. Similarly here, if there is no delta, there is no relative phase difference. That is, if it is like non-oscillating pendulum, then there is nothing happening. So it is delta that is important. I hope this mechanical analogy is able to give you a better understanding of why the delta, the relative phase difference, here the relative phase difference in this figure is labeled as phi, is more important than the Cooper pace itself, right? So we are comparing this to this thing. So delta you can consider as the phi and n as the L, right? So now we talked about a single Josephson junction. We talked about a single Josephson junction, and it has a fixed energy, right? That we are saying is Ij, right? Which has like Ic phi naught by 2 pi. But what we could do is we can take single Josephson junction and we could make two Josephson junctions, which is called a squid. So in squid, we have two Josephson junctions that are attached to each other. And the reason we'd make this is it is hard to control a single Josephson junction. But like if I want one Josephson junction, that is one superconducting pair, one superconductor, insulator, and a superconductor, I have this delta which is equal to like phi 1 minus phi 2. It is hard to control this delta alone, right? But I can make two superconducting junctions like this. That is, I can make two of these Josephson junctions and control the difference of the phase difference. That is, I have insulator, superconductor, insulator. Let us say this has phi 1, phi 2. So this has delta 1, which is phi 1 minus phi 2. And I make another Josephson junction, which has superconductor, insulator, superconductor. And this also has, let's say, phi A, phi B. And this has another relative phase difference, phi A minus phi B. So now I am going to take the phase difference of this delta 1 and delta 2, the phase difference of phase differences. That is what I am trying to do in squid. I have two Josephson junctions and I can control this by applying external magnetic field. So I can tune or I can control this by applying microwave or whatever I want, right? So I can control these relative phase differences rather than controlling on a single Josephson junction. In a squid, I am putting two of those in parallel and I'm controlling the relative phase difference to tune the total frequency. I think we are running out of time,
So,
but basically, yeah,
uh, do they have to be in parallel?
yes.
Why is it so?
we will discuss that in probably it will take some time, but we will discuss that. I have all that here because we want that to add, and we want to control it, right? So why don't we discuss it when we want to add the Hamiltonians like this, and we want to consider this delta 1 minus delta 2, so that we get still the nonlinear oscillator that we can control the 0 and 1 qubit. So basically, we want to add the energies like this. So that's why we want to put them in parallel, so that we can write the Hamiltonian like this.
But
That is
if
the brief answer.
we have them in series,
Then
wouldn't
the
they be?
Hamiltonian won't be this. You cannot add them in parallel, right? Then the Hamiltonian will be different, because you have to consider the way the current is going through one after the other, right?
Yes, yeah. Oh, yes.
Yeah. So we will talk about that. But I want to quickly show before you leave. Once we have squid, then this is how it looks like, the squid. So you see, this is all a superconductor. If I zoom in here, you see here in the orange box here, you see this orange box. In the orange box, what you see, this interdigitals are the microwave guides that are going in. And what you have in between here, that is the squid. That is one Josephson junction here on the left, one Josephson junction on the right, right? So you can see the Josephson junction here, right? So if I zoom in, this is one Josephson junction, this is one Josephson junction. That is the squid, right? And here the Josephson junction is, the bottom portion is a superconductor, this is an insulator, and the top one is a superconductor as well. So you have a superconductor, and an insulator. You see the junction right there. That is the Josephson junction. So I have two Josephson junctions in parallel, and that forms the squid. And I attach that to a gate to CG, and then we will talk about that later. But that's how I actually make a transmon, and I have to put all this into a dilution refrigerator, where in the top you have 55 Kelvin, you go all the way down to, at the bottom you get 10 millikelvin. So what you may have seen in IBM quantum computers is this dilution refrigerator, and so you are going to cool down this transmon qubit that contains the squid down to 10 millikelvin. So we'll talk more about how experimentally we do this, how we prepare this qubit states, and how we can write this qubit Hamiltonian in the next lecture. But what we are getting at is, we're trying to look at the transmon qubit that is actually used in the IBM quantum computer. So I will stop here, and then if there are any questions, I am happy to take. Yes, Saptagiri, the question you have is, we need two Josephson junctions. Yes, we need two Josephson junctions for one qubit. That's correct. You can also have just one Josephson junction, and you can use one qubit, but it will be more prone to noise and harder to control. So even one Josephson junction is non-linear oscillator. So you can get a qubit from there also. But again, it will have like lot of it is sensitive to noise, right? So you want to remove the noise and the decoherence. That is, like if I set it to 1, right? If I pass a microwave, I don't want it to be affected by noise, right? So making 2 gives us better control, because in one qubit, why are they named Transmon? Why are they named Transmon? Okay, I don't actually know. But I will think about it. It is just some name. In physics, usually the names don't mean anything. Like spin means it is not actually spinning, right? So Transmon may have something. I think maybe it has to do with transmission line. I don't know. Because usually like circuits are transmission line models, but I'm not sure. But that won't change the physics of it. So coming back to your question, one Josephson junction, the challenges are controlling the phase difference between the top and bottom. If I have two Josephson junction, I can use an external trigger to control the relative phase differences between two Josephson junction, which I can then use as the dynamic variable for controlling my qubit states. Okay, we'll stop there, and I am happy to take any other questions. If there are no other questions, we will stop here for today. Thank you.